Mapping the Earth's gravity, methods and applications. When we first learned about gravity, we learned about Newton's universal law of gravitation, and then we move on to how gravity affects us here on Earth. So we learned that the acceleration due to gravity here on Earth is a constant 9.81 meters per second squared. We learned that gravity pulls straight downwards towards the center of the Earth, and we also learned that near the surface the field lines are basically parallel. While all of these are good approximations, none of them are strictly true. So let's get on to the details about this. So Newton's universal law of gravitation tells us the force of gravity between two objects. So for a person dropping a marble on Earth's surface, we'll say little m is the mass of the marble in kilograms, big M is the mass of the Earth, r is the radius of the Earth, and g is the gravitational constant, which tells you how strong this interaction is. So this is the force on the marble due to the Earth's gravitational field. But we also know by Newton's second law that a force is equal to mass times acceleration. So when we drop the marble, it's going to accelerate. So putting these two equations together, we can see that little m, the mass of the marble, is on both sides of the equation, cancel that out, and we get that the acceleration due to gravity is just capital G, capital M over r squared, and it's independent of the marble's mass. This was something Galileo noticed a long time ago, that if you drop, say, a bowling ball and a marble, they both fall at the same rates and hit the ground at the same time. So instead of an a, we use a lowercase g usually to denote the acceleration due to gravity. And just putting in some numbers, we use the gravitational constant, we use the mass of the Earth in kilograms, we use the radius of the Earth, and we get that the acceleration due to Earth's gravity is approximately 9.81 meters per second squared. This turns out to be equivalent to a gravitational field strength, because meters per second squared is equivalent to newtons per kilogram. In other words, for every kilogram of mass in the Earth's gravitational field, there's 9.81 newtons of force on that kilogram. If we did this calculation on the moon, we would get a much smaller number because the moon's gravitational field is so much weaker. So what assumptions do we have to make to get to that number? Because we actually did make a couple of assumptions. It wasn't really apparent. One of them was that the Earth is a perfect sphere. And this turns out not to be true. So in addition to surface irregularities, mountains, trenches, the Earth is actually distorted by its rotation and bulges at the equator. And Earth's equatorial diameter is actually 42 kilometers longer than the polar diameter. Another assumption we made is that the mass is evenly distributed. And this is also false. Earth's density, especially in the crust which is close to us, can vary widely depending on the rock, water, oil, gas, other deposits that are down there. So it can differ very widely locally. So naturally you might ask, does this make a difference, and if so, how much? So the actual differences from our theoretical estimate of 9.81 meters per second squared are small, typically plus or minus 0.005%. But we know from studying climate change, tiny differences can make a huge impact when we're talking about global scales. So since these differences are so tiny, small deviations from expected values called gravitational anomalies are usually reported using a smaller unit called the gal. So 100 gal is equivalent to 1 meter per second squared, and in this way we could rewrite g as 981 gal. So I'll let you guess who's the gal named after? That's right, it's Galileo. So, moving on, making a map. The concept of mapping the Earth's gravity dates back a couple hundred years to the early 1800s when Gauss first proposed the concept of the geoid. So the geoid represents the shape that the ocean would take if we just considered gravity and rotation by themselves, and is important to understanding ocean currents and gravitation in general. So in our diagram, 1 in blue is the Earth's ocean, 4 in brown is the crust of the Earth. Number 2, the dashed green line, is what's referred to as the ellipsoid, and that would be the shape that the Earth would take if it was just a perfectly evenly distributed geometric object. So kind of like a squashed sphere, but all the mass is evenly distributed. Number 3 indicates plumb lines, and a plumb line is basically a mass hanging from a string and just indicates the direction that the gravitational field will point in locally. So if the mass of the Earth was evenly distributed, we would expect all those plumb lines to be perpendicular to that dashed green line, the ellipsoid. But as you can see, they're not. And in particular, take a look near the mountain that's sticking out of the ocean on the right side of the diagram. All three of those plumb lines are pointing towards the base of that mountain. And that's because there's so much mass concentrated there. And plumb lines actually behave this way in the regions around large mountains. So it turns out they're not perpendicular to that dashed green line, but if you'll notice, those plumb lines are all perpendicular to that black line, number 5, which is the surface of the geoid, and that's what Gauss was trying to define. So before we had satellites, producing an accurate geoid map was just not possible. So recently, the Gravity Field and Steady-State Ocean Circulation Explorer, or GOES satellite, launched in 2009, was tasked with producing new geoid data that had an uncertainty within plus or minus 0.013%. So this map of the Earth was produced using GOES data, and we'll discuss the lumpiness and what the colors mean in a second. So to measure that, GOES uses really slight changes in acceleration to produce the map data that you see here. So the yellow corresponds to points where the geoid lies above the ellipsoid because there's more gravity and there would be more water pulled there. And the blue area are regions of weaker gravity, and water would kind of spread away from there. So the heights here have been exaggerated in the image to make them a little easier to visualize. And you'll note that lumpy region at the top, where there's really a high concentration of gravity, is actually due to large volcanic deposits of very dense rock along the Mid-Atlantic ridge. And we'll discuss that a little more on the next slide. So this geoid map was also made using GOES data, and as the key at the top right indicates, colors correspond to heights that the geoid would be in reference to the ideal ellipsoid. So this ranges from 70 meters above the ellipsoid, as you can see in red near Iceland by the Mid-Atlantic Ridge, and also in Indonesia and Peru, to 100 meters below the ellipsoid, which is indicated in blue, and you can see a region like that near the tip of India in the Indian Ocean, which has got a lower than average gravity. So the geoid that was produced by GOES turned out to be accurate within plus or minus 2 centimeters over this 170 meter range. That's plus or minus 0.012%. So why was this experiment carried out? I mean, besides providing the most precise geoid map to date, turns out the GOES mission collected the most detailed ocean current data ever recorded, because ocean currents are very strongly correlated with the shape of the geoid. And we all know ocean currents are also strongly correlated to how our climate behaves. So this kind of experiment gives us a really detailed window into our oceans, into our climate, and incidentally, it also gathered data on polar ice sheet thickness and polar ice flow rates. Simultaneously, the GRACE experiment was being carried out, or the Gravity Recovery and Climate Experiment, and that launched in 2002 using twin satellites that orbit at 500 kilometers in altitude and were separated by about 220 kilometers to map how gravity anomalies change over time. So they circled the Earth's poles with a 90-minute orbital period, and in doing so they were able to map the entire surface of the Earth every 30 days until the end of their mission in 2017. So this is a map of the Earth's gravitational anomalies produced by GRACE. And to do it, GRACE uses really sophisticated microwave rangefinders to measure changes in separation as small as 10 micrometers over the 220 kilometer distance that they were separated. So when one satellite passed over a region of higher gravity, it was pulled ahead slightly, and the separation data was then used to map changes in gravity on the order of milligals, or 1,000th of a gal. So as you can see from the key at the bottom, dark red regions correspond to 50 milligals above our expectation, and dark blue corresponds to about 50 milligals below our expectation. And similar regions are highlighted. So for example, the Mid-Atlantic Ridge is again darkish red. The Andes are very dark red. And again, the Indian Ocean turns out to be a spot of weaker gravity in dark blue. So GRACE completed its mission in 2017 and produced a wealth of information on sea level rise, groundwater, movement of glaciers, glacial rebound, hydrology patterns in flood areas like the Amazon basin, and contributions to pure physics like relativistic frame dragging. One of the most pressing findings that came out of the GRACE data was that hydrologists now consider 21 of the 37 largest aquifers in the world as past the point of sustainability, which means they're being depleted as we speak. 13 of those 21 are considered significantly distressed, and this is a potential source of conflict because millions of people depend on these aquifers as their source of their groundwater. One of the most critically distressed actually lies on the border of India and Pakistan, and another one that is critically distressed is actually underneath the Arabian Peninsula, and these are both being monitored closely as potential sources of geopolitical conflict. So, a follow-up to GRACE called GRACE Follow-On or GRACE FO was launched in May, and it's in the process of being calibrated. With even more sensitive instruments than GRACE, GRACE FO is expected to start measurements this August. It employs an additional laser range finding interferometer that is actually the first of its kind ever for any satellite. And it will collect similar kinds of information on hydrology, climatology, glaciology, and other geophysical phenomena. So as you can see from the diagram, GRACE FO actually employs a number of backup systems to help calibrate its range finding, including GPS from satellites above its orbit and from surface-based laser ranging that operates using corner reflectors on the satellites themselves. So in conclusion, gravity anomalies, while small, can tell us a great deal about our world. Most importantly, about the world's most precious resource, its water. Water is going to become an increasingly important issue as our world gets warmer, and time-dependent maps of groundwater may help us plan for or avert disasters and conflicts in the waiting. Many governments have identified water rights as a potential source of geopolitical conflict in the future, and this is a problem that we're going to have to pay attention to very closely. Thank you.